And then I was talking about that. Yeah, I was talking about that too. Yeah.
Okay, so yes, there's gonna be a lot of cyclic structures. We're gonna be getting a lot of them. But okay, let's start with this.
The second example, it made more sense because it was a bicycle.
Yeah, we're done.
That's a good one.
Like, you know, it's like candle, gone.
Okay, everyone. So, let's start calming down. So, okay, last time I showed you guys the general mechanism. It's very simple. You just have three arrows. Two of them make new bonds. The other one just shifts an electron around. So really quickly, do we need a quick refresher on the mechanism? Why not? Okay. So let's pull this up. Okay, so remember, we only need two basic components of the reaction, your diene and your dienophile. Now, your diene is always going to be a conjugated system, okay? And we're only going to talk about those two double bonds. If we have more, they're not going to be really involved in the reaction. We only work with two. Now, next reaction is going to be that you need a dienophile. Now, basic structures of those two things is that diene, you need something that has two double bonds conjugated in the S-cis conformation. And then for your dienophile, you practically just need either one double bond or one triple bond, and that's it. Those are the basic requirements for them. And then for this reaction, we need a little bit of heat, but as the professor said, he's not really going to be mentioning temperature for any of the reactions, so I wouldn't worry too much about it. But either way, we know that the diene is actually going to be our nucleophile, so that means that it's going to be doing the first attack to the electrophile. So that first arrow is just showing that we're attacking our dienophile, and that's making a new bond. Second arrow is going to be from the dienophile to the diene. We're attacking back to make another bond in here. And then to not break the octet, we have to move the double bond over here. And that's the third arrow. So pretty simple mechanism. New bond, move the double bond. That's it. Pretty simple. But let's talk about the certain rules that each of them has. So, okay. So we know that the diene is a nucleophile. Now, I told you that it has to be a conjugated diene. That's the main part. If it's not conjugated, this reaction is not going to work. Now, the other rule for it is going to be that it has to be in the S-cis conformation. Very quickly, do you remember how to find the S-cis conformation? Yeah, so for the S-cis conformation, they have to be pointing to the same side. Now, we know that because we have a single bond in between, we can rotate, we can alternate the conformations between S-trans and S-cis. So keep that in mind. If we see a diene in the S-trans conformation, can you rotate it and make it into the S-cis conformation? If that cannot happen, the reaction is just simply not going to proceed. So keep that in mind. It has to be in the S-cis conformation. Now, the next aspect is going to be a little preference that your diene has, but the reaction can still work without them. And that's going to be your electron donating groups. So let's start writing them. Or sometimes I'm just going to write EDG. They mean the same thing. And we're going to talk about more of those guys later on in the handout, but for now, again, diene has a preference for the donating groups, but again, if it doesn't have them, it's still going to work. It just basically just makes the reaction happen faster, and that's it. Now, for your dienophile, basic structure is going to be an alkene, so double bond, or an alkyne, which is your triple bond. Those are just, again, basic structures. Now, your dienophile is not going to have any specific conformation, so we're just going to cross this out for now. And then the preference for dienophiles is going to be electron withdrawing groups. So let's start writing this here. Again, remember, those are just preferences. The reactions can work without them. Now for our diene, you're gonna have a better diene as long as you have more electron donating groups or stronger electron donating groups, and then same process with your dienophile. You're gonna have a better dienophile if you have more electron withdrawing groups. Now, hypothetically, let's say that our diene has an electron withdrawing group. What do you think is gonna happen to the rate of the reaction? is gonna slow down exactly. If they don't have their exact preferences, the reaction is gonna slow down. Okay, so far, questions on that. We're just talking about conceptual stuff. So far, so good. We're just writing our notes. Okay, today's session is a little quiet. Okay. We're chilling.
So there's no preference for the diene file?
The diene file has a preference to withdrawn groups.
No, I'm talking about like
No preference.
as long as.
As long as you have at least one pi system, you're good. So one double one, one triple one, they're good. Okay, are we ready to talk about the groups more in depth? Okay, some yeses. Okay, so our electron donating groups. Remember, those guys are only gonna be really good for our dienes, not for the dienophiles. So technically we're gonna have a bunch of donating groups, but the ones that you have to know for now are gonna have something in common, which is gonna be the lone pairs and a negative charge. That's gonna be the main feature that donating groups have. So let's just write them in here. Lone pairs, or sometimes a negative charge. And then for the withdrawing groups, it's actually gonna be quite the opposite. No lone pairs and a positive charge. So as long as you memorize at least one of those lists, you can pretty much figure out the other one. It's the complete opposite, and that's it. Now, your professor was talking about how certain groups can contribute by resonance or induction effects, right? Did we get that part? Can someone really quickly explain me what does like resonance contribution or induction contribution means?
In the sense that resonance, the oxygen provides electrons to help push the reaction forward by using a whole pair where it's needed to react.
Okay, that's for resonance.
Inductance, the oxygen itself is like the negative, so it's pulling the electrons towards itself. So force the carbon on the end.
So yeah, pretty much it's just the same rules that we've seen how they apply like so far throughout the semester and in Orgo 1. But let's just write them both in here. So we're gonna have our resonance part and our inductive effect part. So some examples that are gonna contribute by resonance for donating groups is gonna be NH2, any alcohol groups, or for example, any ethers. What do we see in all of them? Lone pairs. So we know that those lone pairs are gonna be moving towards the diene part, making it more electron dense and making it more nucleophilic, okay? And then for induction effects, technically it's gonna be any R group. So that means any carbon chains. And then let's do the same for withdrawing groups. Resonance and inductive effects. Okay, now some examples for withdrawal. Any carbon chains. So a simple methyl group, ethyl group, those guys are gonna be considered donating groups, but they're actually gonna be weaker than some of the contributors by resonance. So keep that in mind. I'm gonna explain you just memorizing this part, which I know it sucks, but it's gonna help you guys for chapter 15 actually.
I thought we established for their inductive effect, there has to be no negative providing that inductive effect.
Technically, the carbon is gonna have a certain electronegativity. It's not gonna be the best, but technically it's gonna be considered to have an effect by inductive effect. Yeah. That was a lot of effects. I wouldn't try to get too caught up on the actual logic. It's gonna be both, but in the sense for this class, at least for this chapter, it's just gonna be withdrawing groups. So again, this part is gonna be mainly memorizing the stuff and by what effect they're basically contributing to the system. Yes. Can you say that again? Resonance and inductive effects, it's same on both sides. A ketone is not gonna be a donating group because by inductive effects, it's gonna be pulling up towards the oxygen. So it's not gonna contribute any electron density to the diene part. And then by resonance, it's just gonna move between oxygen and the carbon from the carbonyl area. So they're not contributing anything to the actual diene. To make a diene better, you need to make it more electron dense.
Also, the oxygen's acting on the carbon and the carbonyl, and then that carbon is acting on the neighboring carbon.
Everything is connected at the end.
Okay, so it's technically carbon that's reacting to that. Okay,
Everything is always connected in a molecule. Okay, let's do the examples in here. So NO2, very important. That's usually the most common one that you're gonna see. We have any halogens. Remember the extras represents halogens. And then we have RCF3. And then by inductive effects, we have a cyano group or any carbonyls. So that's gonna be your aldehydes, ketones, esters, carboxylic acids, those guys. And actually, let's talk about esters and carboxylic acids. Now let's talk about esters and amides. They're gonna be a little bit more special. Esters or amides. Okay, so technically esters and amides can be both donating or withdrawing group depending on the connection. So let's start by drawing out our normal dienophile. So remember, dienophile basic structure is just one double bond, simple as that. Now, let's connect into our ester, for example. Okay, now, between those two, whenever the carbonyl is directly connected to the dienophile, this guy is gonna act as an electron withdrawing group because the carbonyl portion is gonna have a higher effect first. It's gonna affect it first. Now, on the second example, we have that oxygen with the lone pairs first connected to the dienophile. So instead of doing a withdrawing effect, it's gonna be donating. So please remember, those guys are very special. It depends on the connection that they have. So far, questions on that? So far, we're good? Yes. Mhm. It's the whole thing.
Because it's like the double bond is conjugated to one type. You know what I'm saying?
I mean, yes, you're right. There, one of them is conjugated, the top one, and then the other one is isolated, but it's not really because of those systems. It's based on which effect is coming first. The withdrawing effect from the carbonyl or the donating effect from the lone pairs in that oxygen. So it's all about the connection that you have and what comes first. Amide is the same thing. Let's just switch it up in here. Okay, let's do it at the bottom. Let's say that we're trying to get the withdrawing effect first. So it's going to be the carbonyl first and then NH2. But if I want it to be donating, then the nitrogen has to come first and then the carbonyl area. So this guy would be electron withdrawing and the other one electron donating. Again, it's all based on the connection. Okay, do we need a few more minutes to write down our notes? Yes, okay.
You can make it.
Chem? No. Neuroscience and behavior. I already have my batch. Okay, are we ready to move on? Okay, some people are still writing down. One more minute. Okay, it looks like we're good to move on now. So let's start looking at this. So we're gonna be practicing on how to find our dienes and dienophile. So it should be pretty simple at this point. So the very first molecule, and we're gonna be moving on to the right and then to the bottom. Very first one, what is it, diene or dienophile?
Dying.
What about the second one? Dienophile, and it has what kind of group? Which is donating or withdrawing?
Put it on.
It's electron withdrawing, and we have a dienophile. What about the third molecule?
It's a.
It's an ion, so it's a diene or dienophile?
Oh no, it's got an extra pair. It would be a dying.
No. It's gonna be a dienophile. Why? What's the basic structure of your dienophile? Come on, we got it. What was the basic structure of your dienophile? If the diene was two double bonds conjugated,
Isolated. Oh, okay, yeah. We're.
exactly. At least one single double bond or at least one single triple bond. And that's it. We have the basic structure right there. And then the chlorines, where are they gonna be? Electron donating or withdrawing? Yes,
I have a question. So when we say a dying, that's two double bonds. So
yes.
Chlorine or electron.
Yes, they're electron withdrawing. And yes, you're,
so it'll kind of like.
so the third molecule is not conjugated at all or isolated. You just have basically one pi system that's consisted of two because we have that triple bond. But again, basic structure of your dienophile, you need to have at least one double bond. That's gonna be from the main attack for diasolder, and then the triple bond, same process. That's gonna be the main part of the reaction. Yes. Yes, that could be a diene. We just have to rotate it to get into the SS conformation.
Would that be through resonance or through the dying cell?
Which example, second or third?
Third. Third.
This guy, we said that it was gonna be by resonance, technically. But it's technically gonna be more on inductive effects. Because the chlorine is gonna be very electronegative, so it's gonna be pulling away the electron density of the dienophile.
Triple bond, then it's gonna be.
Yes. Okay, fourth molecule. Diene or dienophile?
Dying.
What kind of group do we have? Ether, which is what? Withdrawn or donating?
Structure. Yeah.
Which one did we say?
Donating.
Donating. Because remember, we have those lone pairs in that oxygen. Okay, last molecule in that row. Okay, it's a diene, and what kind of groups do we have? Donating groups. Okay, let's go to the bottom row. Very first one, what is it?
Dying.
That's your diene. Second molecule.
Electron with one. You're dying.
So it is gonna be the dienophile. Because remember, the dienophile portion has to be the triple bond or double bond. That's the only part that's gonna be participating in the actual mechanism. And then the groups are connected in here. So we have two method groups. What are they? Donating or withdrawing? Donating in this case. So we have electron donating groups. Is that gonna be a good dienophile? Why not? What's gonna happen to the reaction?
Slow down.
What is it? Exactly, it's gonna slow it down. That's all you have to know.
Oh, okay. So just because
Exactly. Do not assume that as long as you see a donating group, it's just a diene. It depends. Sometimes it's gonna be part of a dienophile. But remember, if a donating group is part of a dienophile, it's gonna hinder their reaction. Okay, they have their own preferences. If they have the opposite, it slows down their reaction. It's technically done by inductive effects because the carbon is gonna be considered somewhat electronegative. I don't remember the specific number, but you can look it up. But technically, it's gonna be, I don't know, donated in some sort of way. I actually forgot the actual reasoning behind it. He's not gonna be asking for the full reasoning. So yeah. So yeah, guys, as you can see, it's pretty much just memorizing stuff. Okay. And
So-
we're gonna see that in chapter 15 as well. Yes.
So like you said, it's the triple bond is gonna be a dienophile, but not necessarily would it be all electron withdrawing. It can also be.
Donate.
But
Mhm.
if it has the elements of the other category, it'll make it a bad dienophile,
Exactly.
Right, okay.
You got it. Okay, third molecule, what is it?
diene.
Diene or dienophile? How many of you say that it's gonna be a dienophile? Raise your hand. Okay, what about diene? Raise your hand. Just one? So they're actually right. It's gonna be a dienophile because even though that molecule, it is conjugated, remember we have ketones in here. Those ketones are gonna be our electron withdrawing groups. In order to have a diene, we need a conjugated carbon to carbon chain, only carbons. If we see an oxygen, that's not gonna count for the reaction. So,
Okay, I see.
so is that gonna be a good diene? Sorry, dienophile.
Yes.
Yes, we have a lot of electron withdrawing groups, so that's gonna make the reaction happen a lot faster. Okay, the other example, fourth reaction, what is it? Dienophile, exactly. What kind of groups do we have? Withdrawing groups. Very last one, what is it? Dienophile? It's a diene. What kind of group do we have? An ether, which is donating or withdrawing? Donating, exactly. We have the lone person here. Okay, so far, yes.
So for the bottom, reason why that is electron donating is because of, sorry, go to the left.
The triple bonded one.
Triple one, there we go.
So it's because they're all carbons, there's no other oxygen or nitrogen like that, so therefore similarities in electronegativity is what makes it the electron donating group.
Yes.
Got it.
So again, once we get to chapter 15, I'm gonna give you actually a full-on chart based on like how strong the withdrawing effect or how strong the donating effect is gonna be. And that's gonna determine a lot of the products for chapter 15. But for now, we're just gonna wait. Just memorize this quick table that I gave you in here. Okay. Just let's go step by step. I know that it's confusing. But again, really quickly, remember your dienophile, again, main portion is just gonna be that double bond or triple bond that you have. So please keep that in mind. And it's only one pi system basically that you have. So the guys in here. And then where else do we have? Okay. So all of those are your dienophiles. The part that's highlighted, that's just the basic structure. And then for your diene, now I'm highlighting the basic portion of them. Again, whatever else is connected to those highlighted parts, they're either withdrawing or donating groups. And again, diene prefers donating groups. If it has withdrawing groups, it's gonna hinder the reaction. So far, questions on that, on how to identify diene and dienophiles. So far, so good? Okay, I see some people writing down notes, so I'm gonna give you one more minute. Okay, let's look at the next problem in here. In this case, they're asking you for the most active dienophile. So really quickly, what's the basic structure of a dienophile? What do we say? It's just one double bond or triple bond. That's the basic structure. What's the preference for dienophiles?
Proton, positive.
Positive charge, which are what kind of groups? Donating or withdrawing? Withdrawing groups, exactly. So in this case, if we're trying to find the most active dienophile, we're trying to find the one that has the more electron withdrawing groups. If it has donating groups, remember, it's gonna hinder the reaction. So what's gonna be the answer for that one? Do it. D? How many of you think it's gonna be like B as a boy? How many of you think it's gonna be D as a dog? Okay, the ones who chose boy, you guys are correct, but let's talk about it in here. So yes, so first of all, B is gonna be the answer. First of all, we have our basic structure of the dienophile right here, and right here. And then let's go molecule by molecule. Molecule A, is that a diene or dienophile? It's a diene. And then the rest of the molecules are just dienophiles. Now let's look at the groups that they have. For molecule A, those metal groups, what are they? Donating or withdrawing groups? They are donating. Carbon chains, they're donating groups. What about molecule B? What kind of groups do we have? We have 2 withdrawing groups, which makes a dienophile really active. Then molecule C, what kind of groups do we see? Donating. We have those lumpers in the oxygen. So it's not going to be the best reaction for option C. And then last one, option D, we have the triple bond connected to a carbon chain, which is withdrawing or donating. It's donating. Remember, carbon chains, just pure carbon chains, they're donating. So that's why D is not going to be a better option than B. Yes. Yes. That was in the table. So that's why I give you that as a little hint for you guys to remember. Lumpers donating. Positive charge withdrawing. Carbonyls withdrawing. Carbons donating. Okay, so for questions on this, on how to identify the most reactive dienophile or diene.
Second most dienophile would be
It would actually be D. Why did you say D?
pi bond, so more electron donating.
So yes, and not only that, it's about the reactivity of the donating groups. Something that has lone pairs is gonna be a strong donating group versus a carbon chain that doesn't have any lone pairs. That's gonna be a weaker donating group. So in that case, between C and D, we have 2 options. One of them is that D is gonna be a better dienophile because it has more electrons overall, and then also because of the donating groups. It has weaker donating groups, basically.
So if there wasn't that second pi bond there, and it was just an
It
L,
would still be D.
it'd still be
Yes.
because the electron pairs on carbon.
So yes, remember, maybe I should show you the chart for chapter 15. Okay, let's quickly pull out the chapter 15 handout. Let's do this. Okay. Try not to focus too much on the resonance and reactions that you're gonna see in there. Just focus on that chart in the highlighted area. Okay, just focus on that part. I'm gonna give you that chart in chapter 15. Don't look at it. Don't take a picture right now. Okay, don't take a picture right now. But okay, let's talk about this guy. I mean, you can do that, but you might get confused. That's the thing. You guys can take a picture, but you might get confused with this. Okay, so we were talking about our groups and we had an ether on the other side, right? Molecule C, it had an ether. Okay, so molecule C had an ether. Now, in this case, just so we're all on the same page, As you move to the left, you're more reactive, which means that you have a stronger donating group. So we can see that an ether is gonna be a stronger donating group than just a simple R group. Now, if we're talking about a diene would be better if it had an ether. Why? Because it's a stronger donating group. Now, if we're talking about dienophiles, the complete opposite. First of all, dienophiles do not like donating groups. So if we need to choose, we need something that's really weak, which in this case is weak. Again, if we compare ether with a carbon group, the carbon group is gonna win for the dienophile. Okay,
It doesn't like donating group because it's preventing the attack.
exactly. Okay, so did that clarify some of the questions now?
So the presence of the ester actually is making it a better.
You can draw it out if that helps. Okay. So hopefully that answers some of the questions. Again, all this based basically on the order of reactivity for the different groups, for both donating and withdrawing groups. But again, I'm not gonna put that chart on this handout yet because it might confuse you. It's gonna be more useful for chapter 15. Okay, so let's go back to our handout. Okay. Do you have any other questions on this problem? Are we good? We're all good? Okay. Let's look at the next two. They're asking for the most reactive dienophile on the first one and for the most reactive diene on the second. So I'm gonna give you 3 minutes to try and figure it out. You guys can talk with each other, use your notes. Again, 3 minutes. It should be pretty simple at this point.
No, time out. There should be one. There's 4 electrons. Carbon, donating. Yeah. Never mind.
Okay, alright,
I have to double check that.
Alright.
Mm. Okay, did we find the answers? No, not yet. We were just talking. Okay, so let's talk about the first problem, the one that's asking for the most reactive dienophile. What's the answer? 3? Do we all agree? On the left side. Do we think it's 3 as well? Yes. Okay, so what does molecule 3 have that the other molecules don't have? Carcinate network, yes. So that's cyana group. This is gonna be your electron withdrawing group. And remember, that's the preference for dienophiles. The methyl group, that alcohol, what are they? Donating or withdrawing?
Donating.
Donating. Okay, and then if we're talking about the most reactive diene, the second problem, what's the answer?
We got 4 for this
Do you all agree? You got 4? Okay, I feel like yes. Okay. So yeah, these two guys, what are they? Donating or withdrawing? Donating. What could be the second molecule that we could possibly use as a diene, a reactive diene? Do you all agree it's not gonna be molecule 3?
Yes, we both
Yeah,
use
yeah,
that.
because we said that the ketone is withdrawn.
I mean, by definition, we could also use one, but it would be less hindered because, I mean, yeah, because the methyl.
Because it has
use the
ketone
methyl.
versus the carbon.
No, I'm talking about the one methyl on the left on one. Would that hinder the reaction? Like, it would still work for one, but it would be hindered. So-
Somewhat. Okay, so let's start with molecule 3 first of all. So carbon chain, that's donating groups. Then we have a carbon chain that has an alcohol group that's still donating. Now on molecule 1, we have our carbon chain. This is donating, and then we have COH. What functional group is that? It's an aldehyde. What are aldehydes? Withdrawing or donating? Withdrawing. Carbonyls, they're withdrawing. So-
Aldehydes withdraw.
Aldehydes are withdrawing. Any carbonyl groups, they're directly connected, they're gonna be withdrawing. The only special examples that we saw were with esters and amides. Okay. Okay, so far, any other questions on this? So far, we're good. Okay, now. Let's look at the next problem. Donating, yes. Yes.
Ah.
It's Monday, so you know. Okay, so let's look at the next problem. They're asking which of the following dienes can undergo the reaction. So we have to remember the rules.
Oh, it has to be a super,
Super cis, exactly. And remember, if it's in the S trans conformation, can you rotate it? Can you not?
You can.
Oh, you can heat it, oh, that's right.
It's not in a, like, compound. Not locked in.
Mm-hmm.
Okay, so. You can't work.
Oh, you said, I think it's feedback. Oh, yeah, it has to be, super thin.
Oh, right.
And
PEA, which one is gonna be the best one?
So, see it, you can see it. Alright,
We think it's A.
There's like two.
It's A.
where, no, you know what, I think, for the simple fact that.
Bro, A. There's like 3 super cis.
Oh, but you can't rotate, you can't make it.
You want the super cis.
Okay, do we have a
Oh, I see what
final
you're saying.
answer?
Okay.
No,
Not yet, we're still thinking about it.
Oh,
I'm gonna let it play out, I'm gonna hold my breath.
oh, oh.
Bro, you went all in.
Okay,
You went
so-
all in on it. All in on it, like,
So really quickly, this might answer some of your questions. Now, when we said that our groups were electron donating groups, I just meant single bonded double bond, sorry, single bonded carbons, okay? Just a metal, isopropyl groups, everything is single bonded. But if you see any double bonds or triple bonds, they're very electron dense, so they're gonna be electron withdrawing. So think about it.
So it's E.
You think it's E? Think about every single aspect of reactivity in a molecule, not just the rules that we just went through.
oh, I hope that-
Think about everything.
Pushing the reaction. And the double, and the single bonded,
Yeah.
double bond can like twist right there.
Yo, yeah. Yeah, I second that. It's
Nobody second, I third.
Okay, but what's the answer?
E.
Elephant.
Molecule E? What do we think? Do you agree? We're gonna stick with A. Okay, so let's start with the ones that are just not gonna be good dienes. Which molecules would they be?
B.
What's the conformation for molecule B?
That's
It's super trans. Can we rotate it? No, because it's part of that cyclic structure. I can't rotate it, so it's not gonna be B at all. What about molecule D? What conformation is that? Super trans as well? Can I rotate it? Nope. See, I can rotate it. So first of all, what conformation is that molecule shown as? Super trans. Now I have a single bond, so that means that I can rotate it into the SS conformation. Now, let's look at molecule A, for example. Molecule A. Molecule A, okay. So that one, what kind of conformation is that? SS, S trans. Technically, yes, you're correct on that part, yes. We have, so yeah, S trans is right here.
And you got two of them.
SS is over here. Now, even though, no matter what kind of conjugated part you're looking at the molecule, we have those what are they? Those double bonds. So we know that they're gonna have a little withdrawing effect, so it's not gonna make the best diene. So that's why we're gonna be discarding option A. Okay, now we're between C and E.
Wait, why'd you say it's not A, I'm sorry? Okay. that's-
Too much resonance, yes. Okay. Oops. We're between C and E. Okay, so we have single bonds that we can rotate. Now, most of you said molecule E, but did we consider steric hindrance as a factor?
I was thinking about it because it's like you have all that bulk and then it like when you rotate it, it's like.
It's
Part
too
of it.
crowded.
Yeah.
Option E is too crowded once we rotate it. So the answer was actually option C. We have those rings, but overall it's gonna be less sterically hindered for the actual attacking diacetyl there. So please consider everything, not just the rules that I wrote down in those charts. Think about everything, especially steric hindrance. Like that's gonna be your answer most of the time. Okay, so far questions. We're good? Do we see why C was the answer and not E?
Yeah. No, I was.
Oh, I didn't do two. Yeah, they're electron withdrawing. So think about everything. Okay, let's start with our actual reactions. We have 6 minutes, so I'm not gonna be talking about endo and exit today. So I will be covering that on Wednesday. And that's when we're most likely gonna start chapter 14. Okay. Now, do you wanna do one reaction before we leave? No, please no. We're a little too tired from lecture. Okay. Okay, we're gonna apply all of the rules on Wednesday, and we're gonna start chapter 14 as well. It's a Monday. It's a Monday. It was a rough weekend for everyone.